Good morning, everyone. If you're on the Zoom meeting, can you hear me? All right. I think it's time to get started. My poor computer is struggling with keeping up with Slack and Zoom and OBS and the Twitch mod window. So we'll see how well this works. All right. So welcome to day 2 of distributed systems. Last time we only did logistics and administrivia and stuff like that. Today we're actually going to get to the course content. So the first thing I want to talk about is what exactly are distributed systems? So this is going to be a question that we try to answer as a group. What is a distributed system? So I want to give one answer, which is actually a funny answer from Leslie Lamport, who is sometimes thought of as the father of distributed systems. He's done a lot of the foundational work in distributed systems, and we'll talk about some of that soon. But Leslie Lamport said, a distributed system is a system where I can't get my work done because some computer that I've never even heard of has crashed. And he was kidding when he said that, but there's actually a lot of truth to that because, well, let me pause for a second because folks aren't seeing the document camera on Zoom. I'll share it also. Cool, so you should now be seeing the document camera on Zoom. Thanks for pointing that out. All right, so Lamport's definition of distributed systems, which was a joke, actually ends up having a lot of truth to it because it's about failure. And as we'll see, distributed systems are characterized by failure. So I want to give a definition that's slightly more serious. And this one comes from a guy named Martin Kleppmann, who he's the author of a book called Designing Data-Intensive Systems. And if you happen to look at the course website, there's actually a nice illustration on the course website, which was created by him, and he defines a distributed system this way. So this is Martin Kleppmann's definition. So a distributed system is running on several nodes. And you can just think of node as meaning a computer connected by a network. And then the other key part of this is that it's characterized by partial failures. So what do we mean by partial failures? So what I mean by it is that some parts of the system might be broken while other parts of it are okay. And furthermore, it's often impossible, it's at least impossible for the software to know what exactly is broken. So what do I mean by impossible for the software to know? Well, we'll come back to that. So to get a little bit more specific about what I mean by nodes here, so I said you can just think of a node as being a computer, but maybe a more formal way to define it is we can say that a node is an instance of some software running on a computer that communicates with other nodes, which are also instances of software running on some computer, in order to accomplish some task. So there are some things that students kind of brought up in the past when I asked this question about what is a distributed system. Um, and the things that they brought up were like things like, oh, a system where work is distributed fairly, or multiple computers behaving as a single computer. And these are good answers, but they're also, I think, very optimistic, right? Like, okay, like ideally you want the work to be distributed fairly, right? And ideally you might want multiple computers to behave as though they're a single computer. Uh, but in practice, distributed systems are kind of rife with failure. And so I like the fact that that this definition kind of brings failure to the forefront. So let's try to go into a little bit more detail about what this partial failures thing is about. So if you want to answer a question, you can do so either in chat, or you can do so, if you're in the Zoom meeting, you can do so by voice. I ask that you please keep yourself muted unless you're talking. Uh, so actually, does anybody want to take a stab at this? Like what would be an example of a partial failure? What do you think that I mean by that? Sure, okay. Ha. So yeah, so there's a couple of different things that people are suggesting. So um, network partition. Yeah, we're going to talk more about this soon. So if you have a network of machines, different kinds of failures can occur, right? Like one kind of failure is just one of those machines crashing, but it's also possible that you could have a failure even without any machines crashing because the connections between the machines fail. So that's one possibility. Uh, some other people are suggesting the machines themselves crashing, right? A drive failure, a physical failure of the machine. Some other people are suggesting some more um, uh, intermittent failures, like particular messages being dropped. So I think the thing to keep in mind is, and then also software misbehavior. So we'll talk more about that soon. So I think the thing to keep in mind is that by partial failure, we mean that some of the things that are that's supposed to be part of a computation happen and others don't. So this is different from the kind of failures that we're often used to thinking about with a single machine. So on a single machine, uh, often if part of, let's say, the operating system fails, then it all fails. So that's what a kernel panic is. And the way that the system is designed is so that if part of the OS fails, right, then it will kernel panic and you'll have to restart, right? There's no there's no way to kind of continue to operate in the presence of that kind of failure. So treating this kind of partial failure as a situation where you have to kind of keep going in the presence of a failure, this becomes more important when you have many machines, right? If you have just one machine, right, and something fails, then it's not so bad to have to just restart, right? So, but if you have, let's say that you have 4 machines or 400,000 machines, and let's say one machine fails. Well, you don't want to have to take all of the machines down and start the system over completely in the case of one of those 4 or one of those 400,000 machines failing. You really want the rest to be able to keep operating in the event of such a failure. And in fact, the more machines that you have, the more inevitable it's going to be that some machine is going to fail. So if you didn't allow the system to keep running in the presence of partial failures, then a system of many, many hundreds of thousands of machines would be completely unusable, right? Because at that scale, something is always going to be failing. So your system must continue to work in the presence of failure, because otherwise it would never work at all. So the probability is pretty high that something is broken. So if you failed whenever something broke, then no work would ever get done. So this philosophy of kind of continuing to operate in the presence of partial failure. So I think of this as sort of the cloud computing philosophy. So we can kind of distinguish between between different philosophies. So cloud computing versus, let's call it HPC, or high performance computing. So the HPC philosophy is more like the philosophy of choosing to treat partial failure as total failure. So in the HPC philosophy, if something does fail, then you might start the computation over completely from scratch. And there's typically, because failures are common in a system of many machines, typically an approach is taking that involves what's called checkpointing, which means every so often you save your progress. And then if a failure does occur, you roll back to wherever it is that you checkpointed. So that's one philosophy. And those systems are also considered distributed systems. But we're going to be spending more of our time talking about this, this so-called cloud computing approach, which involves working around partial failures. And expecting those kinds of failures. Questions about this so far? So let's start to talk about some examples, right? Let's start to talk about ways that failures can occur. So as people have already pointed out, in addition to machines themselves failing, connections between them can fail, right? So let's look at an example of that. Let's say that we have a very simple situation where we have, let's say, two machines. So let's say we have a machine M1 and another machine M2. And let's just say that M1 wants to ask M2 a question and get a response. So let's say that M1 wants to know what the value of X is. So M1 asks M2, hey, what's the value of X? And let's say M2 happens to know or believe that X is 5. So then hopefully M2 would send back 5, right? In this simple scenario where there's two machines and there's one request and one response, what are some of the things that could go wrong? What do you think? Message never sent. All right. So yeah, so it's possible that a message didn't get sent or just gets lost somehow, right? So let's say that, so we'll say this. If the request from M1 gets lost, why would it get lost? I don't know. Maybe a backhoe took out the network cable. But for one reason or another, the request from M1 could get lost, right? So then there's another possibility, right? Which is that this request from M1 is just slow. So you could have M1 ask, what's X? and this message starts to get sent, but then M2 is waiting and waiting and never actually receives it, or it takes a long time for it to receive it, M2 can't wait forever, right? At some point, it has to make a decision, right? So this slowness could happen for a number of reasons. It could happen either in the network between M1 and M2, or it could also happen in some sort of a message queue, either on M1's side or M2's side. But for whatever reason, maybe M1 thought that it sent the request, but then M2 never received it for whatever reason. Another possibility, right, is that M2 crashed, right? So M1 sent the message, and let's say that the message even actually arrived, and then M2 immediately crashed. So if that happened, let's say that any of these three things happened. Does M1 have any way of knowing the difference between these three situations? No. So from M1's point of view, none of these situations are really distinguishable from one another, even though they're really quite different, right? So the first situation, could be due to a backhoe taking out the network cable, right? The second situation could be due to congestion on the network. The third situation could just be because M2 kernel panicked, right? It could have nothing to do with the network, or it could be a lot of different reasons. So, but even though all of these situations are drastically different from one another, from M1's perspective of trying to understand, and maybe from a human's perspective on M1's side who's trying to debug this problem, all these situations are totally indistinguishable. Here's another situation that's indistinguishable. Let's say that M2 doesn't crash, but let's say that M1 sends the message, and M2 is just slow, right? So in this case, maybe M2 has the answer, but it's having trouble looking up the answer because it has to go to disk or something like that. So maybe M2 is just being slow. Maybe M2 is being slower than M1 expected it to be. And in that case, maybe M1 decides that it's never going to get a response from M2. So that's another issue. Or then maybe M1 actually sends the response, right? But this time, the message is slow. And so M1 never actually gets the response, or the message gets lost. So there's like a backhoe here, and it takes out the network cable, and then our message gets lost. So all of these situations are completely different, right? But they all basically look the same from M1's point of view. So going back to the first one again, so the request in the first place could get lost, or the request could just be really slow, or the machine that you're sending the request to could have crashed, or the machine that you're sending the request to could be slow, or the response could be slow, or the response could get lost, right? So from M1's point of view, you can't tell the difference between any of these things. So this is very important. If you send a request to another node and you don't receive a response, it is impossible to know why. I'm actually going to write that down because it's so important. In particular, it's impossible to know why without global knowledge of the system. Which you don't have. So there's a bunch of horrible things that can go wrong. Is there anything else that could go wrong in this M1, M2 scenario? Sure. So okay. So M1 could crash in the first place, right? I guess if M1 crashes, uh, then that would be distinguishable on M1's end from a situation in which M1 doesn't crash. Um, so some people were saying things in chat a little while ago about messages becoming corrupted, uh, or cosmic rays flipping bits. So those are actually real possibilities. Or M2 could lie, right? M2 could be a bad actor and could refuse to answer the question or could lie. So those sorts of things, like M2 lying, refusing to answer, um, cosmic rays, um, those sorts of things, etc. Those are known as Byzantine faults. And we'll talk about that a little bit later in the course, a little bit. So how do real systems deal with this sort of situation? If one machine wants to send a message to another machine, and it doesn't know for sure if it's going to get a response, what does M1 do in practice when it's sending out a request and it wants a response? Okay, so some people are asking questions like, well, in this example, we said that M2's knowledge of X is that it's 5, right? So one person's question is, well, what if M1 asks for the answer, right? And then M2 sends it, and then it changes soon after that. So yeah, that would be yet another situation. And that so we're only talking about a network of 2 machines, right? But suppose that there were a third machine out there, M3, that also had the ability to send messages to and from M2 and could update the value of X. So in that case, sure, the value that M1 gets might be stale by the time it gets to M1. So we're going to talk about that much, much more later in the course. That's going to be one of the most important issues that we discuss, in fact. So we'll talk about that. But the kind of the point of this example is to show that even in this very simple scenario where we only have 2 machines, there's a whole lot of uncertainty on M1's end. So how do real systems deal with this? So I would say, in reality, what M1 has to do if it's sending a message to another machine is have some sort of timeout. So what's a timeout?
It's like a set amount of time before you drop a request.
Right, yeah. So for us, it means after some amount of time, if M1 is sending this request, if there's no response, give up and assume failure. So that's kind of our best tool in reality for dealing with these situations often. But why might it be a mistake to assume failure? Well, what if it's something like this? In this case, so far we've just been talking about M1 asking for the value of x. So M1 is just asking a question and getting an answer. But what if it's a different kind of a message, right? What if it's this? What if M1 actually caused a side effect on M2? So let's say the message was like increment x. And then the response from M2 was okay. So if M2 was originally had x set to 5, and then this increment occurred, and now x is 6. So if M1 doesn't get this okay response, you don't know whether the increment happened. So if you get the okay response, you can assume that the increment occurred, right? Assuming no Byzantine faults. But if you don't get that okay response, it would be wrong to assume that it did occur, and it would also be wrong to assume that it didn't occur, right? Because the failure could have been the one where M2 sent the message back and then the message got lost, right? So in that case, X could already be 6 over here, and M1 would just never get the confirmation. So in that case, if M1 sent this message out and never got a response, M1 wouldn't know whether the increment happened or not. So it's not really safe to assume that it did or it didn't. And this sort of uncertainty is a fundamental characteristic of distributed systems. So although timeouts can be really useful, right? In this case, let's say this message does get lost on the way back from M2. So M1 has sent this increment X message and it set this timeout, right? It never gets the response, and so the timeout expires. But that doesn't mean that M1 can assume that the increment didn't happen, because it's also always possible that the failure happened on the way back from M2. So there's as we'll see when we talk about more in the course, we're going to find that this sort of uncertainty and this fundamental uncertainty that we have is inevitable in distributed systems, and there's kind of one way around it. Questions about that? Somebody asked in chat, what are cosmic rays? Yeah, so it's there's a pretty good answer in chat, actually. Somebody points out cosmic rays will cause the bits in a machine to flip, causing a machine to have differing values than others in the same system for no reason that's kind of debuggable using the tools that we have. So, so one of the biggest causes of uncertainty in this example is network latency, right? And if we knew for sure that there was some sort of maximum delay on messages in a network, then that would allow us to rule out certain kinds of failures, right? So for example, let's say that you know that, that the maximum amount of time that it would take a message to get from M1 to M2 is some number D. And then let's say that the maximum, and that's the maximum delay, let's say, for any message in the network. So that's the maximum delay of a message from M1 to M2 or from M2 to M1. And then also the maximum time, let's say that M2 could spend processing a request is, let's say, some number R. So if that were the case, let's say that the maximum delay of a message in the network is D, and let's say that the maximum processing time that M2 spends responding to a request is R. So in that case, what should the timeout be on M1's end? How long should M1 wait? Yeah, it's 2D plus R, right? Because the time that it takes for the message to get from here to here is at most D. R is the maximum time the message takes on this end, and then D again is the maximum time that it takes on this end. So that would rule out certain kinds of uncertainty that we had before. So it would rule out the kinds of uncertainty that have to do with slowness, right? So we two of the kinds of uncertainty that we talked about were the message from M1 to M2 just being slow, right? Or the message from M2 to M1 being slow. So those would be ruled out by that. But that still leaves a lot of kinds of uncertainty that we still have to deal with. It still leaves the machine crashed scenario, and it still leaves the possibility of the network connection just going out. Um, and and furthermore, most of the time we don't actually have this sort of guarantee about a maximum delay. Sometimes we make a simplifying assumptions in systems that we build, and we assume that there is a maximum delay. But on the internet in general, that's not actually true. So my colleague Peter Alvaro likes to say that in distributed systems, we have to deal with, not only do we have to deal with this partial failure problem, but we also have to deal with unbounded latency. Not only that, but uh, not only does he say that, but he actually, this is actually how he defines distributed systems. So this is Peter Alvaro's definition. So in distributed systems, we have to deal with both partial failure and unbounded latency, and that's what makes it so hard. Okay, so we've talked about what a distributed system is, and we've given a couple of different definitions. What about why? Why would you want a system like this, given how clearly terrible they are, right? Given how hard they are to debug and build, why would you want a distributed system? So somebody in chat, a couple people in chat say scalability. What does that mean? So one reason is maybe you have no choice, right? So if you have more data than can even fit on one machine, then you need to have a distributed system. So if you're Google, you have no choice but to do distributed computing all day, every day. And then the other possibility is that even if you aren't dealing with data at that scale, maybe you want to make things faster. And sometimes you can do that by using more computers. So we'll talk about that more later on in the course as well. So I'm still wondering. So a couple of people asked, or a couple of people mentioned scalability. So what does that mean? Well, one of the things that it means is this first point, right? So scaling could involve scaling to more data, right? Uh, Another possibility is um, scaling to more users, but more users can also mean more data, right? Uh, some other people are pointing out things like redundancy. Yeah, so this isn't necessarily um, so so redundancy doesn't necessarily mean that the system has to be distributed, right? I could have multiple copies of something, but have them just be on one machine. But that doesn't necessarily help if that machine crashes, right? If I want my redundant copies to actually fail independently, then I need them to be physically separate in some way, right? And the more physically separate that they are, uh, the less likely it is that their failure is going to be correlated. So that's yet another reason why you might want things to be distributed. So at this point, I want to pause and do a quiz question. And so we'll pause for about 3 minutes, and I'll put up the link to the question in chat. So if you're on the class Slack, you should see this quiz question coming up. The form will now automatically collect your email address as you fill it out, which means that you have to be logged in uh, um, to your UCSC Google email in order to fill it out. Oh, some people are saying the form is closed. Just try refreshing it. All right, we'll give it a few minutes. All right, over 100 responses already. I'm going to leave it open for a little while longer, but let's move on. So we started to talk about timeouts a little bit, and that kind of brings us to our next topic, which is time and clocks. So my colleague Peter, when he's lecturing about this, he likes to start by asking, what is time? But seriously, what is time? Like, what do we use time for? Or what do we use clocks for? Does anybody have any like particular suggestions about what do we use clocks for? And this doesn't even have to be specific to distributed systems. What do we use clocks for in computing? To synchronize stuff is a suggestion. So yeah, so we use clocks to say when something will happen, right? So that we can rendezvous. So so one thing that clocks are for is to mark particular points in time. So this class starts at 9:20 a.m. PDT. That would be an example of marking a particular point in time. Or this item in my browser cache expires on April 1st at 3 o'clock p.m. Or this error in the log file has a timestamp of March 13th, 11:56 a.m. So those are all particular points marked in time. So that's one thing that clocks are for. What else are clocks for? So what about timeouts, which we were just talking about a second ago? So timeouts are for discussing durations or intervals of time. So this class is 65 minutes long. So that's an example of an interval. Or this request will expire in 30 seconds, right? This request will time out in 30 seconds. That's a timeout like we talked about. Or this user spent 4 minutes and 9 seconds on our website. Those are all examples of measuring durations or intervals of time. And both these are pretty useful, right? So computers have both what are called time of day clocks and monotonic clocks. So let's talk about the difference between those. So a time of day clock tells you what time it is. It's usually synchronized between machines using NTP, which is the network time protocol. And time of day clocks are bad for measuring durations or intervals. So if these are the things 1 and 2 that clocks are used for, time of day clocks are bad for measuring durations or intervals of time. Why? Why are they bad for that? Yeah, so clocks, for one thing, clocks might not be perfectly synchronized between machines, right? So NTP is pretty good. NTP stands for Network Time Protocol, um, and it does a pretty good job, but it's not, it doesn't necessarily mean machines are absolutely synchronized. But one reason why this is bad for measuring durations or intervals is because the time of day time can actually jump backward and forward. So either due to things like daylight savings time, uh, or for other reasons. Um, this is the number 2, in case you can't read it. Um, so time of day clocks are not what you want to use for implementing timeouts. They're not what you want to use for implementing something that has to measure a duration or an interval of time. What about timestamping particular events? Well, time of day clocks are okay-ish for that. But only okay and not great. And the reason why it's only okay is because, again, clock synchronization is only so good. And we might need some more fine-grained sort of resolution to prevent certain kinds of bugs. And we'll talk more about why that's true soon. So those are time of day clocks. So given that time of day clocks are bad for durations or intervals of time, and they're only okay for marking points of time, they're not going to be the kinds of clocks that we use much in distributed computing. You can maybe get away with them some of the time for marking points in time, but if you try to do that, sooner or later you'll run into problems. So then there's monotonic clocks. So monotonic clocks only go forward. So a monotonic clock is going to be some kind of counter. And maybe it counts up, let's say, milliseconds since the machine was restarted, right? And so if you use Python, for example, you can, if you import the time library, there's a mechanism that you can use for a monotonic counter. And if you check what your monotonic clock says at a given time, it's not going to have anything to do with what your neighbor has if they check the same thing, because its absolute value is meaningless and not comparable between machines. So it doesn't help you at all in terms of marking particular points in time. It's completely useless for timestamping particular points. So it's bad for purpose 1. But it's good for purpose 2. Because if what you need to do is time out after a certain number of milliseconds, then it'll work great. Yeah, so so Unix timestamps are a monotonic clock, and so you can actually do this experiment yourself in Python if you do import time, and then you call time.monotonic. You can check and see what your monotonic clock on your machine says. So. And I think it's just the number of milliseconds since your machine's been running. So which of these kinds of clocks are useful in distributed systems? Well, so monotonic clocks, right? Because we can use them to implement timeouts. And as we saw, timeouts are something that we often need. But timeouts but monotonic clocks aren't useful for comparing between machines. So, okay, so we've got a way to implement timeouts, and that's great. We have monotonic clocks. By the way, if you tried to implement monotonic, or if you tried to implement timeouts, rather, using time of day clocks, you would get into big trouble, um, not only with things like um, uh, daylight savings time, but also with leap seconds. So if you're curious about a fun distributed systems bug, go look up the Cloudflare leap second bug. What they did was they actually tried to implement timeouts using time of day clocks. So that kind of leaves us, with this question, right? So we have a way of measuring durations or intervals of time that works reasonably well for distributed systems. But this question of how to mark points in time is still open, right? We don't necessarily have a good way of doing it that's using these kinds of clocks. So now is probably a good time to point out that the kinds of clocks that I've been talking about so far are what are called physical clocks, right? So both of these kinds of clocks, time of day clocks and monotonic clocks that I've been talking about so far, are physical clocks. In distributed systems, as some people in chat have already anticipated, we can't get away with just having physical clocks. We need a different notion of clock, which is called a logical clock. So this in physical clocks includes both time of day and monotonic clocks. Logical clocks don't do the same thing that the clocks that we've just talked about do. They don't measure time of day, and they don't measure elapsed time. Instead, they only measure the ordering of events. We'll discuss this idea a whole lot this quarter. So this is a different notion of clock, right? It's not necessarily what we're used to when we're thinking about clocks, right? So a fundamental question when talking about ordering of events, right, is which event happened before another? And this is going to be particularly important to know, especially when you get into situations like we talked about earlier, when we were talking about communicating between two machines and the possibility that there might be this third machine out there, right, that might be changing the value of this variable x that we're trying to read, right? So one thing that we might want to try to figure out, right? Let's say that M1 is trying to read the value of x from M2, and then some other machine out there, M3, is actually resetting the value of x. Well, we might want to know which happened first, right? Did M3 change the value of x before M1 read it? Well, that's a question about ordering of events. So knowing which event happened before another is pretty crucial to correctness in distributed systems. So this is something that we're going to talk about a great deal this quarter. Let's say that you have two events, right? Say A and B. And they could be anything. They could be anything at all. But yeah, we could say they're like database rights, but they could be anything. And so let's say we have A and B. And let's suppose that I know that A happened before B. The notation that we're going to use for that is A arrow B. So we'll write A arrow B like this when we know that A happened before B. We'll talk about ways to know that A happened before B sooner or later. But what does it tell me? If I know that A happened before B, what does that tell me about causality? What does that tell me about what could have caused what? So there's a couple things you know, right? So if A happened before B, we know that A could have caused B, right? We don't know for sure that A caused B, but we know it could have, right? What else do we know? We know that B could not have caused A. So Peter Alvaro taught this course in fall 2018, and I'm teaching it now. His style of teaching could have influenced mine. Spoiler, it did. But my style of teaching right now could not, at this very moment, could not have been an influence on the way that he taught CSE 30 yesterday or on Monday. So could what I'm doing now influence something that he does in the future? Potentially, yes. So this notion of causality or potential causality, in this case, that A could have caused B and B could not have caused A. This is very important in distributed systems. Why? Why is it so important? Sure, debugging. So yeah, one way that it can help us is debugging. So let's say that I'm looking at my distributed system and I have some sort of bug, right? Let's say that one machine thinks x equals 1 and one machine thinks x equals 5. It's helpful at that point to be able to look back at all of the events that occurred and try to figure out what may have caused x to be 1 or what may have caused x to be 5, right? And this notion of happens before won't answer all our questions, but it will at least allow us to rule out some things that definitely did not cause the bug. So things this is good for. One is debugging, right? So figuring out possible causes of a bug. What else is it good for? So I would say that it's useful in designing systems in the first place. So if you can design a system such that if you know that event A happened before B, then your system will never allow users to observe event B before event A. It's possible to design a system that way, and we'll talk a lot more about this soon. So that's it for today. We'll come back next time, and we're going to talk a lot more about this notion of happened before, and we'll begin to introduce some more concepts. For those of you who are in the class at UCSC and not just watching on Twitch, I have office hours after this. So see you later.